name is Allison Watson.
Hello, my name is Jack Stephenson.
My name is Bella Dunmeyer.
My name is Laura Camacho.
And I'm Ivana Polina.
We're the Lagrange points. At the center of our proposed CubeSat, the Raspberry Pi will act as sort of the hub for everything else going on in the satellite. The solar panel will feed the battery, will feed the Raspberry Pi power. The Raspberry Pi will send power to the IMU in exchange for sensor readings. When the sensor readings indicate that it's a good time to take a picture, the Raspberry Pi will send a signal to the camera informing it to take a picture. The camera will send an image back to the Raspberry Pi. The Raspberry Pi will run an analysis script, and then use the onboard communications to send the summary down to our ground station. Everything will be held onto the chassis with a combination of screws and nylon standoffs.
This is a mechanical drawing made by me in AutoCAD, and it displays the two most important parts of the CubeSat, which are the Raspberry Pi as well as the IMU.
So far, our CubeSat proposal uses the bill of materials shown on the screen. I don't want to hover over it too long because me reading a list gets monotonous rather quickly. Suffice it to say that with the Raspberry Pi required peripherals and the physical frame for the CubeSat, as well as the launch rails and everything else needed to make it fit together, the cost for our proposal is $254.52.
Okay, so our given solar panel has a current of 2 volts and 60 milliamp hours, producing 0.12 watt hours, and our Raspberry Pi power supply can hold up to 10,000 milliamp hours, and our Raspberry Pi has a total power consumption of 4.5 watts. Our IMU has a power consumption of 0.041 watts. Our camera has a power consumption of 0.125 watts. So our total consumption per hour is 4.67 watt hours. Therefore, our charging time required for 1 hour on will be 38.92 hours.
So we have photo analysis that is going to be saved into a text file, and our ways of how we're going to collect our data, which are significantly below the budget. And for this part, we're going to be using Python and HSV in order to be able to find the plastics inside of the ocean.
Attitude Determination Control is what ADC stands for, and it's a subsystem of the satellite. And it's gonna look at the location of the Earth in relation to the IMU, and it's gonna be able to take a picture and send it through a radio wave back down to Earth. And then Bluetooth communication is gonna review all the images sent from the satellite on the Raspberry Pi, and it's also going to be communicating through radio waves, and it's going to send signals to antennas back to Earth. And then we're going to look at the images that come through the Pi and check the RSSI throughout this process. 256 kilobytes a second is the average uplink rate, and latency is around 638 milliseconds.
Our software plan as it stands today has 3 major states: a calibration state in which the gyroscope and magnetometer have their average measurements taken, a photography loop in which we track our position and orientation over time, and if the gravity vector, which is our indication of which way is down, aligns with the magnetometer's indication of which way down ought to be, and where the camera is known to be facing, we'll take a photograph, analyze the photo on board the Raspberry Pi, ultimately logging some items, and then a final state, which isn't so much a software loop at all, will use the Raspberry Pi's onboard reboot function to disable it for a certain amount of time so that it can charge enough to run the whole process again.
Okay, so there's a few basic components that we have to consider when thinking about a power system for a CubeSat, and those being power source, energy storage, power distribution, and then power regulation and control. Everything is pretty self-explanatory. The power source being solar panels, energy storage where our energy actually gets stored, being our CubeSat's battery. Power distribution is what actually distributes the power into the rest of the CubeSat. And centralized and distributed architecture are two main ways, but since CubeSats are so small, centralized architecture is typically used. And for power regulation and control, this basically regulates and monitors all of the power throughout the CubeSat. So direct energy transfer and peak power tracking are two main ways. Direct energy transfer powers the CubeSat's loads and battery directly, while peak power tracking has an additional box between the panel and the loads.
In the future, we're planning on further developing the code for each subsystem and testing it, which we'll do through May 2nd. We will assemble the CubeSat through May 6th, and test our assembled CubeSat on both May 9th and May 13th. Any discovered problems will be fixed both in between those dates, as well as afterwards through May 16th, because we're sure more challenges will arise. They always do when we're building things. We are doing this in order to have everything prepared for the tech demo on May 20th, and we'll then spend the subsequent week preparing for our final event. As far as what each of our focuses will be during the subsystem design phase, I will be focusing on the main software architecture and planning. Yvonne will be building the power and assembly. Jack will be focusing on the attitude determination and control system. Bello will be working on communication with the ground system, and Laura will be focusing on the imaging and image processing requirements of our goal to detect plastics in the ocean. Our specific SMART goals will have calibration routines for each sensor and a plastic detection method for the camera by May 2nd. We'll have a fully assembled CubeSat, including an IMU camera, Raspberry Pi, launch rails, and all 6 sides, by May 6th. Our assembled CubeSat will be able to take a picture and estimate the amount of plastic in view against a solid background by May 16th. Thank you for listening.